Okay, hi guys, welcome to engineering and structural design. Okay, as we are talking about the practical cases, now we're gonna find this in the second part the maximum positive bending moment and maximum negative bending moment at the cross section C. So first we're gonna find the influence line for the bending moment. The second part is the bending moment. The bending moment. Okay, let's draw the bending moment. So this is the shape of the influence line for the bending moment. This is the positive area and this is the negative area. Okay, we want to find what is the magnitude or the value of this peak here. The ordinate actually is 2 and here also is 2. But how we found it? To find this value, let's consider this simple supported beam. When you have a simple supported beam and then we want to find the bending moment at this position, we have this shape. If you call this part A and this part B, and the total length is L, so to find the magnitude here is A times B over the total length. So we're gonna use the same formula here to calculate it here, but between the portion B and D, B to D. So our A here is 3 and our B is 6 and the total length is 9. So we get 3 times 6 is 18 over 9, we get 2. And to find the corresponding 2 value here, we use the relationship between triangular to find these 2. After finding the influence line for the bending moment, we have now to find the configuration for the applied load. So here is our beam. We have this part, this portion, and we have the big portion. So we have two different type of load. We have a dead load and we have a live load. The dead load is 20 kilonewton per meter, and then this dead load is actually including the safe weight of the beam. So this dead load is gonna be applied on the total length of the beam. So we have 20 kilonewton per meter that is applied on the total length of the beam because it's the dead load including the self weight of the beam. This is 20 kilonewton per meter. Now we know that we are finding the maximum positive bending moment. So we're gonna apply the level load only on the positive portion so that we can find the maximum positive bending moment. And the positive portion is between B and D. So we applied first the uniformly distributed live load of 40 kilonewton, the 40 kilonewton per meter, and then we take the concentrated load, we applied it at the position where we have the maximum height or ordinate. We applied here 90 kilonewton. Now to calculate the maximum positive bending moment at the cross section C, we get this distributed load that is applied on the negative portion is 20 times the height of the negative portion, 2 times the length here is 3 times half. So we get the surface or the area of the triangle. And then this is negative because it's applied on the negative portion. Plus these two concentrated distributed load combined together, we get 60 kilonewton per meter times the area under the applied distributed load, we get 2 times 90 times half. The 90 is the length and the half is the formula for the triangle, plus the 90 kilonewton that is applied at the height, 90 times 2. After doing this, we get the maximum positive bending moment applied at the maximum positive bending moment at the cross section C is equal to 660 kilonewton meter. So we can understand that to design this beam under the bending moment case, we have to find, or we have to consider in the design, the maximum positive bending moment of 660 kilonewton meter. Now we're gonna find the next configuration so that we can calculate the maximum negative bending moment at the same cross section. Okay, to find now the maximum negative bending moment, we have to use our second configuration. So the first, we applied the dead load that is applied along the total length of the beam. And then after that, we have to add now the live load, but the live load is gonna be applied only on the portion where we have negative area. I mean between A and B, so between this area. So we get our 40 kilonewton, that is a distributed load to 40 kilonewton per meter. Here we have 20 kilonewton per meter, and then we're gonna add our concentrated load of 90 kilonewton applied at this position when we have the maximum ordinate, but the maximum negative ordinate in the influence line for the bending moment. After having this configuration, so we are sure that we're gonna find the maximum negative bending moment at the cross section C. So let's calculate the maximum bending moment at the cross section C. So the maximum negative bending moment is equal to the sum of these two values. Here we get 60, but is negative because it's applied on the negative section, times 2 is the height here, times 3 is the length, times the half. Okay, minus 90. 90 is the concentrated load, times 2, and then plus, we're gonna plus now this dead load, but that is applied only on the positive portion. So that is 20 times the area now is 2 times 9 times half here. Okay, so we get this formula to find or to calculate the maximum negative bending moment. After calculation, we get the maximum negative bending moment is equal to minus 180 kilonewton meter. So according to what we just calculated right now, we can conclude that at that section, this beam will be designed by considering one maximum negative bending moment of minus 180 kilonewton meter, and then one maximum positive bending moment of 660 kilonewton meter. So this was the two values we're gonna use for the design to calculate the shear stress and if the structure or the beam is made by concrete. We're gonna use these two values to calculate the reinforced bar and truss and so on. Thank you for watching, and see you next time.